Hello everybody and welcome to our next video in unit 9, which is going to be the relationship between free energy and equilibrium. So we talked about already how the Gibbs free energy tells us whether a reaction is thermodynamically favorable or not. And that's by looking at your value for delta H. And it's also by looking at your value for entropy. So, of course, an increasing entropy is favorable, and an exothermic reaction is also favorable. So that leads to a negative delta G. That excess energy is what can be used in order to do work in other processes, which is what the universe strives to do. However, we can also look at favorability using something else that we've talked about already. And you might not be looking forward to this, but it is the equilibrium constant. Because if you remember, higher values for equilibrium constants tend to mean that a reaction is very product favored. So we can relate our Gibbs free energy to our equilibrium constant right here. And this can also be used to determine the favorability of a reaction or a physical transformation, because again, we could do this for physical processes too. So let's take a look. Let's just compare equilibrium constants to Gibbs free energy. So if I have a value for K that is less than 1, you might remember this. So this is less than 1. If I have a K value that is less than 1, that means that I have more reactants that are present. Because if you remember, my ratio of products over reactants is going to be very low if this value is higher. Okay, if there's a higher concentration of reactants, my value for K is going to be low. If I have a value for K that is greater than 1, that means that that reaction has a higher concentration of products. It is a product-favored reaction. However, if I have equal amounts of reactants and products, your K is approximately equal to 1 or very close to that. The same is true for Gibbs free energy. So if I have a Gibbs free energy that is a negative value, that means, a positive value, delta G is greater than 0. That means that this is reactant favored. It needs more energy than the system already contains. So that type of reaction is thermodynamically unfavorable. So my equilibrium constant, if that's less than 1, and if I have a delta G that is also positive, these relate. Let's drop that. They relate to one another, okay? If I have a product-favored reaction, and if my delta G is negative, that also means that that type of reactant is product-favored, and that's because that is thermodynamically favorable, right? So again, these two, if K is greater than 1, and if delta G is negative, these are also related to one another. If K is equal to 1 and delta G is very close to 0, that again means that you have a relatively equal amount of reactants and products. So not either side is really favored over the other. So there is a relationship between the equilibrium constant and Gibbs free energy. If a reaction is very product favored in terms of equilibrium constant, that means that it tends to have a negative Gibbs free energy. It is very product favored. Okay, so let's take a look here. I have a product favored and I have product favored. So they are related to one another. I also have reactant favored and I have reactant favored. So there is a relationship between them. And this relationship, we could do a derivation to look at this equation if we want to, which we're not going to, but we could. They are related by this equation right here. Okay, so delta G, the Gibbs free energy of a reaction, is equal to negative RT ln K, where K is the equilibrium constant. So R in this case is a new value for R, right? Because I know we tend to talk about R with ideal gas law, 0.08206. There's another value for R, which tends to be more thermodynamic. Okay, R is a lot of different constants in chemistry. But this value is 8.314 joules per mole Kelvin. Okay, that's important. So that other value for R that you might be thinking of, 0.08206, is liters, atmospheres, mole Kelvin. This is for gas laws. Clearly, we're not working with pressure here, so we're not going to use that value for R. This is the same exact equation. However, this just rearranged. So in this case, it's solving for delta G. In this case, it's solving for K. Either way, it's the same exact equation. You do not have to memorize this. This equation is going to be on your equation sheet that's given to you on the exam. So if I know the Gibbs free energy, I can calculate the equilibrium constant. And if I know the equilibrium constant, I can calculate the delta G value. So I'm bringing equilibrium into this now as well. So we're just going to do 2 sample problems and we're going to call it a day with this guy. So let's see. Sample problem 11. Find the value of the equilibrium constant K at 25 degrees for the reaction below. The standard free energy change, delta G, at 25 degrees is negative 13.6 kilojoules. So my reaction is delta G is equal to negative RT ln K. So I know my value for delta G. My delta G is negative 13.6. However, if I consider my value for R has values of 8.314 joules per mole Kelvin. So you do have to be careful again because I have my R is in value for joules and Gibbs free energy is in units of kilojoules. Let's just convert delta G to joules. Just easier to do it that way. Negative 13,600 joules is equal to negative 8.314 joules per mole Kelvin times, let's see, the temperature in units of Kelvin, because we want this Kelvin to cancel, which is 298 Kelvin. And value for this is ln K. So I'm trying to find this value for K here. The way I would solve this is I would solve for this whole entire thing first. So let's grab a calculator and do this together. So let's do negative 8.314 times 298 gives me 13,600, put that there. That's equal to negative 2478 ln K. I'll divide both sides by negative 2478, so negative 13,600 divided by negative 2478 gives me 5.488 is equal to ln of K. Now remember, the way to cancel out a natural log is to raise it to the power of E. Okay, so K is equal to, and if you do the exponential function raised to the 5.488, you should get about 242. This is a unitless number. Remember, equilibrium constants are always unitless. So what does this value for K mean? That this is, in fact, product favored. And that makes sense. If this value is product favored, if my K is greater than 1, look, delta G is also a negative value. So there's more energy to be had to do work for something else. So that value for K and that value for delta G together makes a lot of sense. And that's really how you would calculate something like this. On your exam, remember, you might not have to actually calculate this like this unless it was a free response question. A multiple choice question, you would just have to say, like, how would we find the value for K? Okay, and you would have to manipulate that equation and say, well, what would be the correct way to solve? let's go ahead and try this one. So this is the same exact thing, except we're given those values for delta G. So we want to calculate the solubility product constant here, which is the same exact thing as just a regular old K, but I'm going to use the dissolution process. This example, however, I'm not given the total value for delta G. I am given each individual value. So let's go ahead and calculate the delta G for this whole reaction. And that's equal to your products. So I have silver ions, which is 77.12. I'm not going to do units here. I'm just going to times that guy by 1. Add that to the chloride ion, negative 131.3 times 1 minus the reactant is negative 109.8 times 1 technically. And your answer should be 55.6 kilojoules. So based on this value, my delta G is a positive value. It requires energy in order for this reaction. I need energy from somewhere else. So this is a thermodynamically, I'll say unfavorable reaction. This means this reaction is not really going to proceed, okay? And therefore, I should not have a lot of, silver chloride is not going to dissociate according to this, okay? So if I consider that, if this is a thermodynamically unfavorable process, let's estimate my value for K must be pretty low, okay? So I must have a K value that's much less than 1. Let's see if I get that when I plug my value for delta G in to delta G is equal to negative RT ln K. Delta G is 55.6. Let's change that to joules. 55,600 joules. It's equal to negative 8.314. Still at 25 degrees, so that's 298 Kelvin. Times ln of K. I'm not going to walk you through the math here. If you do this correctly, however, you should get a K value that's equal to 1.77 times 10 to the negative 10th. Now this makes sense. The KSP value for the dissociation of silver chloride is very low. And because this is very low, this reaction, this process is not going to happen. As a result, it is thermodynamically unfavorable. We know silver chloride to be not very soluble. It's not soluble at all, okay? And we know that because its KSP is 1.77 times 10 to the negative 10th. This is not going to dissociate, okay? It dissociates very, very, very little. And we did a lot of work with KSP, if you remember. So the KSP is equal to the concentration of each species. So it'd be equals X squared. I'm not going to get into that right now, but we're bringing together this thermodynamic favorability and equilibrium using this equation. And that's it. That's all you have to know for this unit, okay, for this section. So on that note, I will see you in the next video, which should be all about electrochemistry, which is getting into the fun stuff. So I will see you then. Bye.